Hello, everyone. It's 10 a.m. Tuesday morning. I was just hoping someone would show up. We don't have anybody this morning, but that's okay. I was going to answer questions, of course, like I always do. That's the main point of having these Zoom sessions, so you can get any unanswered questions dealt with. Also, if you have any topics on regarding any of the subjects we're covering in the class, it's a good time for you to clear those up. So perhaps you don't understand how to use that zodiacal diagram where it has the sun and then the earth in its orbit around the sun, and then it has the signs of the zodiac, i.e. the constellations of the zodiac around it. That diagram can be used to predict what constellations you'll see at sunset, sunrise, and midnight, for instance, at any time of the year, roughly. That's a really powerful diagram, as is the uh, celestial sphere diagram. And the reason these diagrams really are so powerful is they are sort of the models that the ancients had in their head, and maybe even in some cases physically built models such as this, because they were so accurate. So by drawing those diagrams, understanding those diagrams, you can actually use them to make predictions, and those predictions are actually fairly reliable. Obviously, I haven't shown you any one other than what you've seen in your book regarding the Ptolemaic model, but you haven't seen any ones by me regarding the planets, because they're a little bit more complicated, which is why they had to do spheres on spheres and equipoints, epicycles, and difference, and all that stuff. So today we're going to learn about another diagram, specifically the diagram regarding the moon phases. So there's a lot of stuff here. We're going to cover basically not only which moon phases are called what, also why they're caused, what is the actual cause of that moon phase. And then we're going to use that to build a model that we can use fairly accurately to predict the rising, setting, and even the time that the moon is the highest in the sky for any given phase. There's a lot of neat questions that spin off of that. You'll see that in your test 2 practice test, and then of course you'll see it in your test 2 as well. And probably you'll see it the rest of the semester, because students usually don't, they do well, but they don't get as high as I'd like. So I like to have around 85% success rate. I get closer to 80, so I keep asking the questions until I get 85%. All my tests are comprehensive, and this is sort of what I call bread and butter astronomy. So it's something that you sort of have to know. It's not this topic that you just say, well, I'll just not understand that. So anyways, let's get started. It's a bummer that nobody's here, but hopefully you all watch the video. So I'm going to go to my document cam, and I'm going to show you a drawing that I've started. And this is a picture of the Earth. I tried to draw a fairly good circle for OCD reasons, really. There's no need for it to be that good of a circle, but I'm a little obsessive compulsive, so I did. And I even made it blue because, of course, the Earth is about 70% water. So what we're imagining is we're looking somewhere in space above the North Pole. So the North Pole of the Earth would be roughly here. And we're really up high or whatever. Well, actually, probably a little bit more over there. But anyways, and the sun is way off over here, way over there. So far that the size of the sun is fairly insignificant compared to the distance from the sun, so that the sun's rays are all running parallel towards us. Think about that sentence a little bit. The sun is so far away that its size is insignificant, its diameter, in other words, is insignificant compared to the distance away, so that all the individual rays are reaching us parallel. Okay, so when you think about that, think about if this was the sun, all the rays come off perpendicular to the surface of the sun like this, right? But we're so far away that we're only seeing this itty bitty piece where the rays are all parallel. So the first thing I want you to understand about this diagram is I want you to sort of guess. I'm going to ask these questions. I know there's nobody here, but that's okay. I'm going to ask these questions in hopes that you guys will try to answer them when you see the video. So if the sun is over here, way over here, and the Earth is here, which half would be dark, i.e. which half would not have the sunlight on it? And my choices would be the top half, the top half, the bottom half, the right half, the left half, the top right half, the top left half, the bottom left half, the bottom right half. So all those are choices. So remember, it's top half, bottom half, right half, left half, top right, top left, bottom right. Those are all possible choices. And I'm going to ask these questions over and over again about halves. So it's good for you to keep those answers in mind. So it's top, bottom, top right, top left, bottom right. Okay. So the question is, which half of the Earth would be dark? So hopefully by now you've thought about it. You've got an answer. I'm going to go ahead and draw it. This is sort of our terminator, if you will, on this. When you look at the actual moon, and the line where the bright part of the moon runs into the dark part of the moon is called the terminator. So I use the same name for this. So this means the left half of the Earth will in fact be dark. And that is in fact the half that is experiencing nighttime. I've drawn an arrow here. That arrow shows that the Earth is actually rotating this way, and that this line should be really perfectly perpendicular to these rays, but either way, you get the point. So this is the direction that the Earth is actually rotating. It's also revolving, but as I talked to you previously, you realize that it only revolves about 0.986 degrees per day. So that's not much motion. But just in case you wanted to know, that motion would in fact take it going this way. Because if you look from above the Earth and the sun, it turns out the sun rotates in a counterclockwise direction. The Earth rotates in a counterclockwise direction, and the Earth revolves in a counterclockwise direction. Okay. Now, in addition to that, the moon orbits in a counterclockwise direction. So you got to remember, whenever you make this diagram, and you should be able to draw it at the drop of a hat. Whenever you draw this diagram, you want to draw it and make sure that you progress your moon positions such that they are revolving around the Earth in a counterclockwise direction. So now what I want you to do is try to think about what parts of the Earth are experiencing what times of day. So for instance, if I draw a person, I'm going to draw him way out of scale. You can imagine he's microscopic compared to the actual diameter of the Earth here, but there's a person. Okay. I want you to think about this person, where he's located, where the sun's located, where the Earth is located with respect to him. And I want you to think about that and think about what time of day he would be experiencing. So the sun appears to be, at least if he happens to be between the tropics of Cancer and Tropic of Capricorn, and happens to be on a certain day of the year, then the sun appears to be and is directly over his head. And that's sort of our definition of noon, and noon is the exact right answer, sort of. It's the astronomical noon, if you will. It's the time at which a vertical pole will cast no shadow somewhere between the Tropic of Cancer and the Tropic of Capricorn. Okay, so a vertical pole wouldn't cast a shadow. Now, we've gone and divided the Earth up into time zones, stuff like that, and each of those time zones are 15 degrees across. So this might be a time zone, for instance, and this would be 15 degrees. That whole time zone would roughly be all experiencing the same time, even though only this one split instant right here is experiencing noon. Maybe this whole thing would say it's noon. So obviously there's some error built in. But that answer is right. It's just an astronomical noon. Okay. Now, what makes the Earth experience daylight and nighttime is the Earth rotating. Remember, it actually is revolving, but that's not relevant because that's only moving about 0.986 degrees per day. So if I drew a line from the center of the Earth to the center of the sun and watch how that line moved, it would move only 1 degree, 0.986 degrees per day. So something like that. So it's not moving very much. On the other hand, the Earth is roughly, it's a little bit overestimate, but is roughly rotating 15 degrees per hour. So this rotation is way faster than this revolution. So you don't have to think about the revolution. You can just picture the rotation. Okay. So what's going to happen is this Earth person is going to slowly rotate at 15 degrees per hour. And eventually he's going to get to this time of day right here. Again, remember, he's infinitesimally small. So that might help you. I also like to use this because you got to remember on this diagram, compared to even when I put the moon's orbit on there, this guy is really, really small. The Earth is really, really small. And in fact, it would be more correct if I drew the person dead center and I drew the Earth as a dot. Okay. And then I drew him infinitesimally small as well. This would be his horizon, the line going through the center of the Earth, perpendicular to his, say, spine. His spine's straight up and down. So we're going to make use of this little part as well. But that gives you a better idea of what you're seeing. Imagine him infinitesimally small and right at the center. Okay. As he rotates, he can see the sun, 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 and then boom, a split second later, the sun's gone. So what time of day do you think this is? Again, I'm giving you a few seconds to answer. Hopefully you've already been thinking about it. I want you to think about it every time I draw the person on here, and try to answer it before I even ask you for what time it is, much less before I even ask you, as well as before I actually give you the answer. So right now I'm saying it went from seeing the sun to not seeing the sun. So we'll call this sunset. Now in our model, I'm going to make that a little different. I like to have nice firm times. So I'm going to say this is roughly 6 p.m. Obviously, you know for a fact that the sun does not set every day at 6 p.m. It changes. But we found out by using this 6 p.m., it actually turns out to give you still fairly accurate results within, roughly an hour. And it's nice to have a firm time to put down. Now I want you to think about the person standing on the Earth right here. So now I want you to think about where he is, where the Earth is, where the sun is, or where she is, whatever. Don't want to be pro one gender necessarily, but anyways, where is this person at, and what time of day would that person be experiencing? Hopefully from the symmetry you've already got the answer, but this time would be midnight. So midnight is a time of day that we're saying. Of course, we're going to call that, it's actually astronomical midnight, just like I told you earlier. This is astronomical noon, so this would actually be 12 p.m., excuse me, and this is 12 a.m. again on our model. Okay. Now, if I continue to ride the Earth past midnight, and then end up right here, I think you can tell I'm going from clearly any side over here. I can't see the sun because the sun is infinitesimal and small and really far away, and the Earth is really big and in the way. But as I get right here, I go from not seeing it to seeing it, and I think you'd all agree that that time of day is, again, on our model, we're going to say that's 6 a.m. Okay. Again, I don't get much loss of accuracy by doing this, so it's perfectly fine to do that. And you can even fill in the times in between. So what time of day would be this one halfway between the two? What time of day would this one be halfway between the two? What time of day would this one be halfway between the two? And what time of day would this be halfway between the two? So I'm just going to put that there, and I'll fill in those answers later. But I want you to think about them. What time of day is this? What time of day is this? What time of day is this? And what time of day is this? So again, we're going to stick to that model though. So I've given you that this time is 6 a.m. and this is noon. So you should be able to guess what time that would be, or figure it out anyways. But I'll fill in those a little later. I'm now going to set up the individual moons so I can label the phases and help you understand that. But before I do, I want you to think something else too. So we have these times of day drawn on the Earth. We have a rough estimate of where you are at midnight, where you are at sunrise, where you are at sunset, where you are at noon. So in maybe one sentence, you should be able to tell me why we experience daylight and nighttime. Hopefully you can do that. I'm going to give you an answer in a couple minutes. And I want you just to be thinking about it. What is the cause of us experiencing daytime and nighttime? So let me start with drawing a single moon phase. So this time I'm going to make the moon green. And I'm going to do that because cartoons used to always say that the moon was made of cheese. And I can imagine a green Limburger type cheese or something. So there's our moon. This is a particular moon. It's at a particular point in space. And I'm going to try to figure some stuff out about it. So the first thing I want to figure out is, remember those answers: top, bottom, top left, top right, bottom left, bottom right. Which one of the sides of this moon is dark? So I think you all should realize by now the answer to which half of the moon is dark is the left half, just like the answer for the Earth. Okay. So now that I've gotten that moon in place, I'm going to go ahead and answer the question. The reason why the Earth experiences daytime and nighttime is actually people are riding a rotating Earth, and they rotate at relative positions with respect to the center of the Earth and the sun. So for instance, when you are between the center of the Earth and the sun, you're experiencing noon. When the center of the Earth is directly between you and midnight, the center of the Earth is directly between you and the sun. I said at midnight, I don't know why I said that. But when the center of the Earth is between you and the sun, you're experiencing midnight. And when you're perpendicular to those two, you're experiencing either sunset or sunrise, because as you ride the Earth, you run from daytime into nighttime, that's sunset, and then you ride from nighttime into sunset into daytime, and that's sunrise. Okay, so the shortest answer for the question is the cause of daylight and sunlight is the relative position of you, the center of the Earth, and the sun. Okay, so another easier way that's not quite as precise is that the Earth rotates us through various brightnesses. All right, now that we have that answered, let's look at this phase of the moon. What I want you to realize again, this moon is actually really far away. In fact, if you take this distance right here, you have to multiply that by 60, and then go from here that many times, 60 times this far away, and that would be where the center of the moon is. So the center of the moon should be way to poop over there, but we're going to just leave it where it is. And what I want you to realize is you can only see the half of the moon that faces you. So when you look at this, you might say, okay, which half of the moon? So there's a new question. Which half of the moon do we get to see at noon for this particular moon? Again, the answers are top, bottom, top right, top left, bottom right. I think you realize now that the half you get to see is the left half. That's relevant because you can see the whole left half is dark, which means we can't see it. And in fact, this is called the new moon. So that's a new moon. And basically, as you can tell, the sun and it are more or less in line with each other. So not only is the dark half of the moon facing us, at that instant in time, that dark half is facing us, but it's also competing with the actual sun's light because it's directly in line with it or very, very close to it within a few degrees, 5 degrees. So we know you can't see the sun during new phase. Okay, but that's what it's called, new moon. And I'm just going to write new on there. Now, I want you to consider another moon phase. So I'm going to try to do it about the same distance away. Let's put right over here. Okay. So now I have another moon phase, and I'm imagining the center being directly above this line, just, so it's a perfect 90-degree angle again. That's important to understanding exactly what phase is. Now, with that in mind, again, I'm going to ask you which half of the moon is dark. Hopefully y'all already know the answer. It's the left half again. Now I'm going to imagine my person directly under it, and I'm going to ask you which half of the moon do we get to see from Earth? Again, the answers are top, bottom, top left, top right, bottom left, bottom right. So which half of the moon do we get to see from this position here, talking about that particular phase there? Remember, it's always the half closest to us. So we get to see the bottom half. So we saw the bottom, we saw the left half on this one, and we see the bottom half on this one. And I think you can see that from our standpoint, it's half dark and half light. You guys would normally call that a half moon. I apologize for continuing to use the word guys. I'm just still in high school. But anyways, you would normally call this a half moon, but in astronomy, we call this first quarter. So I'm going to write right over here, I'm going to write first quarter. Okay, and that's quarter, Q-U-A-R-T-E-R. Okay, now as you might suspect, you also have a second quarter that nobody calls, but nobody calls that particular phase a second quarter, and we have a third quarter, which is really an accurate phrase that we do use. So that's the first quarter of the phase of the moon, and notice we see half light and half dark moon, or half illuminated and half dark moon. I'm going to draw another phase of the moon now. Again, I'm going to try to keep it about the same distance away. Again, probably because of my OCD. Okay, so this one should be right along this line that connects the center of the Earth and sort of the center of the moon, and the center of the sun, excuse me. Again, I'm going to ask you which half is illuminated, assuming the Earth's not casting a shadow on it. And I think you all will agree that the half that is dark is the, yes, left half. Okay, so we're going to shade the left half in, like so. Now I have a left half, and now I'm going to ask you the other question is, which half does this person directly under the moon get to see? And basically everybody on this half of the Earth will get to see the moon at that time, but I like to draw it directly under so you don't get confused by how big this diagram has the Earth being, because really the Earth is teeny compared to that distance. So if I drew you over here, you'd make all sorts of weird conclusions, and you'd think that you could see a little bit of this part of darkness over here, and you can't. So that's why I always have to draw the guy on the moon directly below the moon. So which half does this person on the Earth get to see? I think you've all probably figured that out by now. Again, it's the half facing the person, which in this case happens to be the right half. So the right half he gets to see. So I'll put here is an eyeball, and here is an eyeball, so nobody looks at the diagram later and can't figure out which half we get to see. So we get to see the half that the eyeball's on. Okay, to make it look more like an eyeball. Okay. All right, now I'm going to draw another phase before we get more advanced. And again, I'm going to try to make it the same distance away roughly. So we'll put it right about here. I'm going to try to make it center directly below that terminator again. And I'm going to ask you, for this particular phase, which half of the moon is dark? I think you all come up with the same answer. And that is the left half again. Okay, and I realize I forgot to tell you the name of that other phase, and I'll go back and get that now. So there's a left half. The left half is the dark half. This phase over here, I did show you which half we see. We see the right half, and if you look, the right half is it seems to be completely illuminated. So we would call that full, which is sort of why I just ignored it, because it was like, duh. But anyways, this moon is a full moon. Okay, now we know that one's a full moon, and now we have this one. We got to figure out, well, what half of this do we get to see from Earth? Again, I'm going to imagine myself directly between the center of the Earth and the center of the moon, and say I only see the half closest to me, so I draw the line this way. That separates the half closest to me from the half farthest to me, and the answer is obviously the top half is what we get to see this time. So we get to see the top half, and I think you see in this case it's again half light and half dark, so that might make you think quarter, and in fact it's called the third quarter. Okay, so that's our third quarter phase. those are the main phases. And in fact, those phases are a split instant in time. Now, if you look on a calendar, you'll find it representing like a particular day of the month as new moon, when in fact, it's that instant in time where the center of the earth, the center of the moon, and the center of the sun are all lying in the same plane. Now, the moon could be above or below the line connecting the center of the earth and the center of the sun. That's why we don't get the shadow of the moon falling on earth every time we have a new moon. But in general, it's definitely going to be in that plane. And that's just a split second, because remember, this moon is actually orbiting, revolving around, if you will. It's revolving around the earth at a pretty decent rate, usually around the order of about 13 degrees per day. So yeah, I think it's 13 degrees per day. Anyways, it's actually revolving as well. So it's just that split instant where this moon happens to fall in that plane that contains the center of the earth and the center of the moon. And when it does, that is an instant in time. That's called new moon. Similarly, when the moon goes through that same plane, but this time with the center of the moon outside of the center of the earth and the center of the sun, then it's full moon. So again, that's just a split second time, but on a calendar, they'll say full moon today. So they'll say, like, June 7th is full moon, and that'll be the full moon day. But it is just a split instant in time. Same thing with this first quarter and third quarter. It's just an instant in time where a line connecting the center of the earth and the center of the moon is in fact perpendicular. Perpendicular means 90 degrees to the line connecting the center of the earth and the center of the sun. The first one you come to in the cycle is the first quarter. The third one you come to in the cycle is the third quarter. And as you might suspected, the second one you come to is actually 180. That's the second quarter, which is also called full moon. But again, nobody calls it second quarter. Everybody calls it full moon. Okay. So those four are the ones that are just a split instant in time. The other four phases I'm going to talk about are actually several days long. And in fact, they're from the split second that this one ends until the split second then this one begins. All that time between is one whole phase. Similarly, from this split second to this split second, all this time in between is one particular phase. So we're going to go over those phases now, and I'm going to try to draw them directly over these lines. So now's a good time for me to point out what time of day those lines are. Hopefully you've all thought about it. This is noon and this is 6 p.m., so you might have guessed that this is 3 p.m. This is 6 p.m. and this is midnight, so I think you might have guessed this is 9 p.m. This is midnight and this is 6 a.m., so I think you might have guessed this is 3 a.m. And this is sunrise, which is 6 a.m. and noon, so you might have guessed this is 9 a.m. And hopefully you did, and that's actually the right answer. So I'm going to try to draw those moons, those other four phases, directly above that. And we're going to reason as if all of them are there, even though, like I said, this moon, if the moon was right here, it would be this phase that all these are called. But we're going to treat it as if it's like that, because it just makes the model really nice and easy, and we can quickly get answers. So I'm going to draw a moon right about here. Okay. And I'm going to ask you again, which half is dark and which half is light? Or specifically, which half is dark? And I think you all by now have gotten used to this answer. It's the left half is dark. So I'll draw that half dark. Now the other thing I'm going to ask you is, which half does a person standing right here see? So again, the answers were top, bottom, top right, top left, bottom right. I think you can see the half closest to us is separated by the half, or from the half farthest from us, by this line right here, which is just perpendicular to the line connecting us to the moon. So yeah, this is the line. So we see the bottom left is the half that that's facing us. And when we look at that, I think you can see this bottom left half is mostly dark and a little bit illuminated. That is what we call a crescent moon. So, and this one, just a day before, less of the bright part, or less of the illuminated part was showing. So we call it a waxing crescent. That's Waxing Crescent, Crescent. Okay, so that's another moon phase. Another moon phase, again, I'm going to try to draw it directly above this. Again, which half is dark? That's going to be our left half. Hopefully this is old hat for you folks by now. If I imagine a person directly right here, I got to figure out what line separates the half closest to us from the half farthest from us. Well, I'll go straight along the path right here and then go perpendicular to that, and I get this line right there. And obviously I see that the bottom right half is in fact closest to us. And if I look at this, notice it's a little bit dark, but it's mostly illuminated, and that's called a gibbous phase. And since it was just a little less illuminated, it's still waxing. So this is waxing gibbous. So that's a waxing gibbous phase. Okay, waxing crescent, waxing gibbous. So as the month progresses, notice I used the word month there, we go from new moon to waxing crescent, waxing crescent, waxing crescent, waxing crescent, waxing crescent, first quarter, waxing gibbous, waxing gibbous, waxing gibbous, waxing gibbous, waxing gibbous, full, and so on and so forth. Now I'll draw another phase. This phase I'm going to try to draw directly above 3 a.m. Again, the half that's dark would be the left half. The line separating the half closest to us and the half farthest from us, again, is perpendicular to this line. So it'll be right here. And this one you see is mostly illuminated. The half that's closest to us, which is the top right half, is mostly illuminated. So it is, again, a gibbous phase. I think gibbous translates to humpback in some language. Anyways, this was much more illuminated. In other words, the whole half of the moon facing us was illuminated before, but now less than half is. So this is called waning. So this is waning gibbous. And I'll draw one more moon directly above 9 a.m. Whoa, I drew it with the wrong color. Can you believe that? This is OCD delight here. All of a sudden I drew it with the wrong color and really disappointed myself. Anyways, there's the moon, which is properly green. Okay, again, the half dark is the left half, like so. And the half we get to see, again, is the half closest to us. To figure that out, we imagine a line from the center of the Earth to the center of the moon, and then draw a line perpendicular to that. Again, this just should come natural. You don't have to think in terms of all those perpendiculars. But when we do that, we see the half that's closest to us is the top left half, and it's mostly dark and just a little bit illuminated. So it's definitely a crescent. And it was brighter, so it's still waning. So that's a waning crescent. So that's quite a bit of stuff to figure out, and that's a lot. Like, this is a very good place for you to go ahead and pause the video and take a break, see if you can draw this, see if you can figure out those times of day and label those moons, because we're getting ready to do some more stuff with it, and this gets kind of lengthy, and it's really easy to lose your attention. So now might be a good time for you to pause it, go get you something to drink, grab a snack, or maybe read a little bit in your book, see if it makes sense with what you read. But either way, this is sort of our moon phase diagram. This tells us a lot of stuff. You don't really see it yet, but it tells us a whole lot of stuff. So I'm going to give you a second to go ahead and pause, and then we'll come back and I'll finish up this diagram. I'm going to pause it myself because I'm thirsty. Okay, so hopefully you all had a little break and your mind's mushy again, ready to accept more cool knowledge and stuff like that. So let's get started. So I have a moon phase diagram. We're basically showing the Earth and the direction that it rotates and the direction that it revolves, both of which are counterclockwise as seen from up here above the North Pole, which is what that is. That's supposed to be the North Pole of the Earth, roughly. The sun is way the heck over there, really far away. That's why the rays are parallel. This is really, really out of whack. So as far as the scale goes, because this distance right here should be 1/60th, 1/60 times the distance from here to here. So really, the moon should be really far away, or the Earth should be really, really teeny, maybe a little bit bigger than that blue dot in the middle. Okay, that's important because that's why I keep drawing the person directly below the moon for a given phase. Like, for instance, when I considered the waxing gibbous, I drew the person right at, or I imagined the person right at 9 p.m. When I did full moon, I imagined the person at midnight, so on and so forth, because really the Earth is infinitesimally small compared to, I shouldn't say infinitesimally, but it's really, really small compared to the distance between the center of the Earth and the center of the moon. I've managed to figure out that the rotation of the Earth drags people through various phases of the day. So it is the rotation of the Earth that actually causes the daylight and daytime, daytime and nighttime, where basically as you go from darkness into light, it becomes sunrise. And then when the sun has the ability to be directly overhead, if you happen to be between the tropics, then that's noon. And then when it goes from daytime to nighttime, that's sunset. And again, in our models, we're calling these times 6 a.m., 9 a.m., noon, which is 12 p.m., 3 p.m., 6 p.m., 9 p.m., midnight, which is 12 a.m., and 3 a.m. Okay. And then we came up with a grandiose conclusion. So the big thing here is what causes the phase of the moon. I think the most succinct answer you can say is the relative position of the Earth, the moon, and the sun. So for instance, when the Earth, moon, and sun all lie in the same plane, but the moon is in between the two, then we have a new moon, as you see there. But when the Earth, the moon, and the sun lie in the same plane, but the moon is outside of the Earth and moon, then we have a full moon. And you never have an instance where the sun is between the Earth and the moon, of course. If we have the plane of the Earth and the sun perpendicular to the line connecting the center of the Earth and the moon, then we have one of the quarters. And then, of course, everything in between are waxing crescent, waxing gibbous, waning gibbous, waning crescent. Okay, so that's what we were able to conclude, and we were able from that to see that basically, yeah, the relative position of the Earth, the moon, and the sun is what causes the phases. You can give this a try by taking like a volleyball and holding it up on your hand, in the palm of your hand, in a dark room with just one source of light, and slowly imagine your head being the Earth and the ball being the moon, and slowly rotate your body holding the moon in front of you, and you will see the bright spots on the moon taking the same shapes as crescent, new crescent, first quarter, gibbous, and then full, and then gibbous again, and then third quarter, and then crescent again, and then new again. So just by rotating like that, you can actually experience the fact that the phases of the moon are due to the relative positions of the Earth, the moon, and the sun. All right, so let's make this diagram even more useful. So to do this, what I'm going to do is give you a sense of how long this takes to go all the way around here. Well, it turns out it takes almost basically 30 days to go around there. But if I'm going to assume this is, 3 p.m. and this is 6 p.m., why not take a little liberty with how many days it takes? And let's use a number that works really well. So the number I'm going to use is 28. We're going to assume that it takes about 28 days to go from new moon back to new moon again. You'll see in your book it's actually like 29 point something or whatever. But the important thing is new moon to new moon is a very specific amount of time. But in this model, we're going to pretend it's. Had a hard time saying that. Sound like Porky Pig. Anyways, we're going to pretend it takes 28 days. So on day 0, we have a new moon. And then remember, all these days between we're treating it like a calendar too. So this whole day 0, is going to be new moon, even though, as I told you, it's just a split second in time. But all the days in between it and this one will be waxing crescent. And because I chose 28 days, I think you can see that a quarter of 28 is 7 days. So this should be day 7. I'll put it right here. And 2 quarters of 28 days is day 14. and 3/4 is day 21. Okay. So that means this is days 1 through 6. This one has days 8 through 13. This one has days 15 through 20. And this one has days 22 through 27. And this one also has the 28th day. Okay. So again, when I use this model, I'm going to pretend it's dead center. So really, I'd call this day 3. I'd call this day 10. I'd call this day, let's say, 17. And I'd call this, say, day 24. Okay, so when I'm working with a model, I'm going to imagine it being directly over that 3 p.m. or 9 p.m. or 3 a.m. or 9 a.m. time. But when I go to state answers, I got to remember it could actually be any of these days in between, not just that one I chose. So now that we've got this, and believe it or not, even though I introduced a couple days worth of error over a month, I really still have a very, very, very accurate model. So what I'm going to do is use this model to predict the rise time of the moon. I'm also going to use it to predict what time the moon crosses your meridian, and that's fancy speak for it goes due south of you and therefore is highest in the sky at that point, and then what time that moon for a particular phase again will set. And I'm going to use the little cutout to make it a little easier for you, even though I don't use this in general in my classes, and I certainly don't use it in my mind. In fact, once you go through this model once and make all these predictions, it might take you 2 times, but once you do it, you're probably not even going to need to draw the model anymore, because you'll find a pattern. And if you find a pattern, don't share it with someone, because if you do, you're ruining their chance to find the pattern. And the pattern that they discover is way, way, way better for them to keep memorized than it is for them to try to memorize someone else's pattern. So each of you try to look for a pattern as you fill out all these rise times and set times, and make it your pattern, and you'll probably be able to remember it and not draw the diagram. That being said, draw the diagram as often as you need to figure it out. Okay. So let's first think about the new moon. So the way I want to do is I want to figure out what time the new moon will rise. And I want to find out what time it looks like it's highest in the sky, which essentially is the time at which I'm directly under the moon on the diagram, or the person's under the moon on the diagram. And then I want to figure out what time it sets. So in order for there not to be any ambiguity, I always start on this model at a spot directly where the moon is directly below my feet. In other words, on the opposite side of the Earth from the moon. So if I'm talking about new moon, I'm going to start over here at midnight, because notice there's no ambiguity. There's no way in heck this dude's seeing my moon, right? Because the Earth is in the way. It's literally like below my feet, right? So what I then do is I ride the Earth until my eastern horizon, which remember is, this spot over here, until my eastern horizon just hits the moon. So as I ride like this, I see the eastern horizon hits the new moon right then, which I'm right here now. See, that's where my head is. And you see that 6 a.m. So here's another reason we don't get to see the new moon. It rises at the exact same time the sun does. So from that, by starting on the opposite side of the Earth from the moon, I was able to find the time at which the eastern horizon just clipped the sun, just got to the center of the sun, and looked at where I was, and that gave me the time of day. So I know that the new moon rises at 6 a.m. Again, that's in our model. You could say accurately, no matter what, it rises at sunrise. That's the hallmark of the new moon. Okay. Now, if I rode until the moon's directly above his head or her head, boom, I get right there. So I say my meridian crossing, M, is noon. diagram's getting kind of busy. It's easier to do this on a board than it is on a piece of paper. So I got the rising time at 6 a.m., the meridial crossing at 12 p.m. Again, meridial crossing means several things. I can disguise it by saying, what time of day is the new moon highest in the sky? Or what time of day is the new moon due south of you? Or what time of day is the new moon directly above your meridian? Or I just say, what time of day is the meridial crossing for the new moon? All those are the same way of asking this question, and it's noon. Okay. Now I'll wait until the western horizon hits the moon, and then I'll be a set time. Because look what's happening. We're literally slipping over the Earth such that we're going to the opposite side, the side where the Earth is in my way. And of course, just like when the sun was over here, that was sunset. But now when the moon's over here, that's also moonset. So I'm going to say the setting moon for this phase is at 6 p.m. So 6 a.m., 12 p.m., and 6 p.m. are the rising, meridial crossing, and setting times for the new moon. I have a little bit more room when I go to do the first quarter or the third quarter. Obviously, you can see there's going to be problems with one or the other because it's not quite big enough sheet of paper here. But anyways, let's do the first quarter now. Again, I want to start on the opposite side of the Earth from the moon we're doing. So I'm doing this moon right here. I want to be on the opposite side of the Earth from the moon. That would put me right here. And what time of day is that? Hopefully you see it's 6 a.m. And again, I'm starting here because there's no ambiguity as to whether I can see the moon or not, and I'm trying to ride it. This time I'm going to do it without the yellow thing to see if that helps you too. So remember, this person is really, really small. Now, in this case, you can really say almost infinitesimally small compared to the radius of the moon, of the Earth. So this person is really, 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 really small. But they're going to ride this, and they're going to ride the Earth, ride. Can't see the moon, 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 cannot see the moon, cannot see the moon. And then you get right about here. Remember, the moon, the Earth is actually really, really small compared to this huge distance, and I am really, really small compared to it. So basically, I'd be standing here, and if the sun were over there, I would say, oh, this is sunrise, but it's not. It's the moon's over there, so I call it moonrise. So the first quarter moon rises at noon. Another way you can think of it, if it just helps you, is when you make a 90-degree angle, the line with connecting you to the center of the Earth makes a 90-degree angle with the line connecting the center of the Earth and the center of the moon. See that 90-degree angle? So that's when you go either from seeing the moon to not seeing the moon, or not seeing the moon to seeing the moon. That's, again, also why I use this figure right here. If I started over here on this side of the Earth and rode until my eastern horizon hit the moon, you'd see, oh, that's noon. So the first quarter moon rises at noon. Okay. So I'm going to write rises at noon. I still got to find my meridial crossing, and I still got to find my setting time for those phases. Let me adjust this too so I can get a little bit more. Whoa. Let me get a little bit more paper space in there. Yeah, that looks good. Okay, so I now have a rising first quarter moon at noon. If I continue to ride the Earth, now I'm here. I'm riding. Tell me what I'd normally do in a classroom is I'd tell my students to stop me when the moon appears to be possibly directly overhead. So I ride. And this is where they would say, oh, right there. Hopefully you guys are doing that too. Directly above my head, which is the meridial crossing, appears at 6 p.m. Again, that's our model time. But reality is the first quarter moon will exactly appear at sunset. Okay, that's exactly true, but 6 p.m. is what we use in our model. And then finally, I ride the Earth, so I see the moon, boom, moon just disappeared. That's the moon setting, and that, of course, is at midnight. So that's 12 a.m. So we now have the times that the new moon rises, crosses your meridian, and sets. Okay, so the first quarter, or excuse me, the new moon did 6 a.m., 12 p.m., and 6 p.m. And then the first quarter rose at noon, sat at crossed your meridian at 6 p.m., and then set at midnight, 12 a.m. Now I can do day 14, which is the full moon. So for the full moon, again, I'm going to do it without the little yellow guy. I start with my person on the opposite side of the Earth from the moon. So I'm doing the full moon. So I want my person to be over here. That person is experiencing noon, and clearly I cannot see the moon because it's directly below my feet, and there's this ginormous Earth in my way. Okay, so I'm experiencing noon. The moon is below my feet. I can't see a thing. I write it. Boom, I hit that 90-degree angle, right? So I'm either going from seeing it to not seeing it, or not seeing it to seeing it. In this case, I'm going from not seeing it to seeing it. So that's my moon rise. So since I'm right there, the moon rose at 6 p.m. So rises 6 p.m. Again, the actual exact right answer is the moon rises at sunset. Okay, that's something you can see readily the next time we have a new moon, or excuse me, a full moon. If you look up in the sky, you might look and you'll see, oh wow, look at the moon. It looks like it's completely full. And then you look across the opposite side of the sky and you'll see the sun's up too. If that's the case, then you know for a fact today is not the full moon, because the full moon has to rise at exactly the same time that the sun sets. So the fact that both of them are still up says you probably have at least another day. Well, probably do have a day. You might have two, but at least another day before the full moon occurs. So it does rise exactly at sunset, but we're going to call it 6 p.m. Now, again, I'm writing. Let's imagine the tip of my pen is the person, or me, for instance. So I still see the moon. 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 I still see. Oh, now all of a sudden the moon appears to be directly overhead. Again, if I happen to be at the right place on Earth, the moon would be above my head. But it's definitely going to be its highest point in the sky, and that's called the Meridian Crossing. And that, of course, occurred at midnight. So I'm going to say Meridian Crossing at 12 a.m. Okay. Now I'll continue writing the Earth. I still see the moon. 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 Boom. I just get to that 90-degree angle again. 90-degree again. So I went from seeing the moon to not seeing the moon. So this is, in fact, moon set, and that occurs at 6 a.m. So the moon set at 6 a.m. Okay, you guys might even be seeing a pattern by now. If you are, that's great. Again, don't share it, but if you are, that's great. We haven't even done these though, so don't get too excited yet. Let's do third quarter. So in the third quarter moon, I need to find the rise time, the meridian crossing time, and I need to find the set time. Okay. So this time I'll use the little yellow guide just in case that's more helpful to you people. Again, the rule is you start on the opposite side of the moon, or opposite side of the Earth from the moon. So I'm looking at third quarter, opposite side is over here. So I'm actually experiencing around 6 p.m., but I'm definitely experiencing sunset. Clearly over here, I can't see the moon because it's directly below my feet and the ginormous Earth is in the way. So I write it until the eastern horizon just lines up with the moon. So ride, boom. Notice the eastern horizon just lined up with the third quarter. So I see that's in fact at midnight. And lo and behold, I have the rise time for the third quarter moon is midnight, which is 12 a.m. anti-meridian, which means before the meridian crossing. Okay, and that's for the sun, by the way. Now I ride again until the moon appears to be directly overhead. Ride. ride, boom. Right there is when the moon appears to be directly overhead. I see that sunrise, which is in our model 6 a.m. So I'm going to say 6 a.m. for the meridian crossing. Don't forget that meridian crossing can be hidden by words like due south of you, highest in the sky, directly above your meridian, all that good stuff. And then I'm going to ride until the western horizon lines up with the moon. Boom, 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 boom. Right there. That is the moon set. Notice I'm experiencing noon. So the time that the moon sets is 12 p.m. Now, these models are going to be really surprisingly accurate, especially over a matter of a couple weeks. And if you do a little math, you can figure out how much it changes per day and stuff like that. And that even gets you, you can even get a couple months in advance, and you'd be surprised. It's still fairly accurate. You can predict, what phase is going to happen up to say 45 days from now. So that's kind of neat. You might miss exactly the details of exactly what day the noon or the new moon was, or the first quarter, or third quarter, or even the full, but you'll be close on just about everything. So we've now done those main phases. What I'm going to do is, instead of walking you through that process with well, I'll do it with one of them. I'm going to walk you through the process with the waxing crescent, and only the waxing crescent. And then I'm going to just write the answers for waxing gibbous, waning gibbous, and waning crescent. And as you've already seen in some of the reflection questions I posted, I expect you to be able to draw this diagram and make these predictions and stuff like that. So this will be a perfect opportunity for you to do that and figure out, how did I get the answer for that? How did I get the answer for that? And how did I get the answer for that? So with waxing crescent, we're going to do it just like we did all the other ones. We're going to start with the person on the opposite side of the Earth from the moon. Well, the moon is here in waxing crescent. Notice how I'm pretending it's right on that third day as opposed to the first day or the sixth day. Now, on the opposite side of the Earth from the moon would in fact be this time right here. So it's 3 a.m. So I'm going to use my pen this time and say, all right, I'm going to wait till I make that special 90-degree angle. That's where I go from seeing to not seeing, or not seeing to seeing. Currently, right now, it's clear that this person at this particular location has no hope of seeing that moon, because the Earth is in his way and the moon is below his feet. So as I ride, I can't see, boom. Now I'm 90-degree angle. I go from not seeing to seeing, and I see that the time of day is 9 a.m. So the waxing crescent rises at 9 a.m. Again, you might remember, hey, waxing crescent is actually the day after the new moon as well. So that day, it might actually only rise, since this one rose at 6 a.m., waxing crescent might have actually rose at 7 a.m. on this day. But again, all our work, we're going to account it for here, but just be advised, it's perfectly normal to find a waxing crescent up at, just coming up at 8 a.m. or 7:15, stuff like that. But this is on sort of average, if you will. Now I continue to ride the Earth until the moon appears to be directly overhead. Ride. Boom. Right there at 3 p.m., that moon appears to be overhead. So my meridian crossing M is 3 p.m. This is a 9 in case people can't read my writing. Okay, and then again, ride until I make another 90-degree angle, because I know it goes from seeing to not seeing. Then boom, 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 boom. Boom, 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 boom. So right there, I see that I went from seeing to not seeing right at 9 p.m. So it sets at 9 p.m. So the waxing crescent rises at 9 a.m., crosses your meridian at 3 p.m., and sets at 9 p.m. So for the rest of these, I'm just going to write the answers. Okay. So again, I have a pattern that I've found. I've actually found several patterns, and I don't even have to draw the diagram anymore for me to figure it out. But basically, this moon will rise at 3 p.m. Feel free to guess ahead of time before I put the answer down. It'll cross your meridian at 9 p.m. and it'll set at 3 a.m. The waning gibbous will rise at 9 p.m. It'll cross your meridian at 3 a.m. and will set at 9 a.m. And finally, the waning crescent will rise at 3 a.m. It'll cross your meridian at 9 a.m. and will set at 3 p.m. So that's it. That's the complete moon diagram. Okay, that lets you know the rise time, set time, all sorts of cool stuff. Really, really good stuff there. Again, this is a lot of information. This would be a perfect time for you to take another pause. I'm going to do a couple more things, but you really probably need to take a break because we've covered so much information. You should even maybe take a screenshot of exactly what this diagram looks like. Hopefully you got enough resolution that you can see it pretty clearly. Because these times will be questions that come up on your test. And if you try to, by the way, if you're trying to memorize them, forget about it. The stress of a test is going to kill you. You can certainly do it, but it's going to be really, really hard and prone to a lot of error. But if you learn using this model by, drawing this diagram with all the days and times and risings and meridian crossings and phases, all that stuff on that diagram, if you do that at least once, but sometimes it takes 2 or 3 times, you'll probably find a pattern that you can use without even drawing the diagram anymore. So anyways, this is a good time for you to pause it. I'm going to pause for a second too to get a sip of coffee, and I'll finish up what we're doing in a second. Okay, I've had a little break myself, and hopefully you guys have taken one as well. Either way, like I said, you should have paused it and taken a little break. Even if you haven't now, go ahead and do it. I went ahead and used the time also to write up a question that I'm going to ask you guys just to see how powerful this model is. And it's kind of a a neat little thing that I like to show. The other questions that you get on tests are simple questions like, what time does a waxing crescent rise, or roughly what time would a waning gibbous be highest in the sky, or what time does a new moon set? Those are just straightforward questions. I'm going to ask you a really good question, and I have a ton of them. I make them up all the time. So I want to make sure you can use this diagram that way. So let's go to the question. So first off, remember, we've got this diagram. I'm going to refer to it a couple times, but then I'm going to just go to a separate sheet of paper and draw some other things to help you figure out the rest of the question. So here's our question, and I apologize if you can't read my writing that well, but or my spelling, because I'm often a horrible speller. But anyways, I don't think I made any mistakes, but who knows? I'm a goober. So, all right. So a stunning buff astronomy instructor with a full head of hair. Yeah, I'm referring to myself, y'all. It's clearly y'all understood that. A stunning buff astronomy instructor with a full head of hair is returning from a date with his beautiful bride, Shawnee Bear. That's my wife's name. That's my nickname for my wife. Yeah. It's a Facebook thing. Anyways, when he notices a fingernail clipping shaped moon directly out of his passenger side window. The moon is low in the sky and it's 4 a.m. What phase is the moon in? How many days until the full moon? What time will this particular phase of the moon set? And then finally, this is the coolest one of them all. Which direction was he driving? So, a stunning buff astronomy instructor with a full head of hair is returning from a date with his beautiful bride, Shawnee Bear, when he notices a fingernail clipping shaped moon directly out of his passenger side window. The moon is low in the sky, and it is at 4 a.m. What phase is the moon in? How many days until full moon? And what time will this moon set? And finally, which direction was he driving? So when I look at this, I realize fingernail clipping, if you've ever clipped a fingernail, you probably know that thing that flies out and then your mom or dad or somebody comes and gets on you because you're making a mess of the living room or whatever. Looks like that. So to me, that looks like a crescent. So that's sort of a way I can hide the language. In other words, I don't have to say a crescent moon because that would give you or cut your choices down to 2. I'm just going to say a fingernail clipping shaped moon or something like that. So clearly, I think you guys will know it's either like that or that. And of course, this one would be, if you see that, it's certainly a waxing crescent. If you see this, it'll be a waning crescent. I might bring another model up later on to show you why I know that one will be a waxing and this one will be a waning, but not for right now. So we know now that it has to be either waxing crescent or waning crescent. Well, we saw that it was low in the sky, and basically the moon is low in the sky for like the first 3 hours. after rising, and it's low in the sky again for the last 3 hours before setting. And about the 6 hours in between, I consider it sort of high in the sky. So that's just a rule of thumb that you'll like to use over and over. So if I look up here at Waxing Crescent, I remembered that I saw this out my passenger side window at 4 a.m. Well, at 4 a.m., this moon's not even up yet, right? It rises at 9 a.m., reaches meridian at 3 p.m., and then it's set again by 9 p.m. So it's not even up. So hopefully it's going to be this one, but you know, your instructor, it could be a goober and just completely made a mistake. So you always want to double check that. But lo and behold, when you look, indeed, the waning crescent rises at 3 a.m. So clearly it would still be low as late as, say, 6 a.m. Maybe even you might push it to 7, but roughly I use 3 hours as a rule of thumb. So clearly it is low in the sky at 3 a.m., so it must be a waning crescent. So the first answer, A, is waning crescent. Now the second answer, it asks, when will the next full moon occur? So how many days until full moon? So you might say, well, Mr. Younger told me I treat this as if it's dead center. So dead center would be 3 days after day 21. So I'm going to say that's day 24. And this is day 28. So 25, 26, 27, 28. That's 4 days until the new moon. But I want to find out when the full moon's occurring. That's another 14 days ahead. So I would say the answer would be 14 plus 4, which is 18 days. That's probably the best answer. But to be honest with you, any answer between 15 and 21 days, excuse me, between 15 and 20 days would be acceptable. So the nominal answer would be 18 days, but I would accept 15 days, 16 days, 17 days, 18 days, 19 days, and 20 days. I would not accept 21, nor would I accept 14, and I think you see why. So that's how we predict how many days until full moon. When I said what time will the moon set, well, we figured out that the moon was a waning crescent and it sets at 3 p.m. So the fourth answer would be, or the third answer would be 3 p.m. Now, the hard part is how do we actually get which direction he's driving? So I'm going to use a picture on the back here. So let's imagine this is north, this is south, this is east, and this is west. News, NEWS. Isn't that neat? Anyways, we know that the moon was low in the sky. It, in fact, had just rose, and everything rises in the eastern half of the sky. So we saw it out the passenger side window. So we know the moon should be over here in the eastern side of the sky. It might be a little north of east. It might be a little south of east, but mainly it's probably about due east. So what we're going to do is draw our car and make sure the passenger side points that way. Well, here in America, we drive on the left side of the car. So the driver's seat, if the car is going north, the driver's seat would be here. If the car is going south, the driver's seat would be here. So if I put the steering wheel here, then that's the passenger side facing east. So clearly that's the answer. So we'd say part A, the answer was waning crescent. Part B, the answer was 18 days, but I would accept 15 to 20 days. Part C was 3 p.m. And part D, I would probably say north, but someone might actually argue that it would be northwest or even northeast. I would actually accept any of those because you can make an argument that it would be south of east or west of east, especially if you've recently seen one. It turns out that the orbital plane of the moon is about 5 degrees different from the plane of the sun. So, you know, that's actually why we don't get those eclipses every year. I mean, every month at new moon and full moon. So that's how you go about answering that question about which direction. Obviously, you see there's a little bit of ranges of answers, but these questions, when I do them, are normally multiple choice, so you just choose the best answer. So, you know, I would have like a 18 days here. I wouldn't have a 16 day, a 17 day, and an 18. They would not be the choices because that would be unfair to you. So that's how you deal with that. The other thing that's neat about this diagram, I think you can see, is the only way that we're going to have the moon blocking the sun from our vision, which means the sun has been eclipsed, so it's a solar eclipse, is when the moon is in new phase. So we can only get solar eclipses in new phase, but that's a necessary condition, not a sufficient condition. Like I said, the plane of the moon's orbit is basically different from the plane of the sun by about 5 degrees, and only if you happen to be on one of those nodal points, which is where the moon happens to lie in the same plane as the ecliptic, are you going? It's only at those times that you're going to actually get an eclipse. So sometimes the moon will be above the sun, sometimes it'll be over to the right of the sun, sometimes it'll be over to the left of the sun, sometimes it'll be below the sun. But every now and then you will get the sun, the moon, and the earth to all line up, not so that they're all in the same plane, but they're all really close to being along the same line. When that occurs, then you have a solar eclipse, and basically the moon's shadow truncates downward to essentially an infinitesimally small spot on the earth. It's on the order of 700 miles or whatever, so it's not small compared to humans, but it's small compared to these distances. And that particular shadow will go across the earth following the path of the moon's shadow, and everybody in that little line will get to experience a solar eclipse. If you're outside of it, you're going to get a partial eclipse, that sort of thing. So what's necessary for a solar eclipse is a new moon, and the moon has to be at one of its nodal points, or another way of saying that is the sun, the moon, and the earth have to lie almost in the same line. There's a little variance. You could be just a little bit off and still get a eclipse. Also, this orbit is not exactly a circle. It's actually an ellipse. So there are times where the moon is closer to us, in which the moon would be so big that you wouldn't see any of the sun during an eclipse. And also there's a time where the moon is farther away, and I'm grotesquely overestimating or overemphasizing how big the difference is. It's a really small difference. But if it's too far away, then it won't be big enough to actually completely cover the whole disk of the sun, in which case you get an annular eclipse if you happen to be in that spot where the shadow is. So you can get this moon varying in size, even though in general the moon and the sun are both half a degree in diameter in the sky. This moon can sometimes be a little closer and it'll be a little bit bigger than a half a degree, and sometimes it'll be a little further and it'll be a little bit smaller than a half a degree. So it can either completely engulf the sun's image, in which case you'll get a really black solar eclipse, or it can barely or come short of covering the sun, in which case you get an annular eclipse. Similarly, if you want to know about a lunar eclipse occurs when the Earth's shadow engulfs the moon, so the moon is eclipsed. So that's a lunar eclipse or a moon eclipse. That can only occur, of course, you can see from the diagram, the sun's over here, the moon's over here, the shadow would go this way. That can only happen during a full moon, and it doesn't happen every full moon, again, because you have a roughly 5-degree tilt between the plane of the moon's orbit and the plane of the ecliptic. So that is when the moon actually appears sort of a ruddy red. Some of the light is actually bent through our atmosphere and allowed to hit the surface of the moon. That's why it's not completely black. Remember, the moon doesn't actually produce its own light. It's not in the visible spectrum anyways. So it's only illuminated by the sun. So if our Earth casts a shadow on it, it's not going to get the sunlight, except for the small amount of sunlight that gets refracted through the Earth's atmosphere to hit the surface of the moon. So the necessary conditions for a lunar eclipse is a full moon, and again, the moon at one of the nodal points, or another way of saying that is the moon, the earth, and sun all line roughly or very close to being on the same line. Okay, so that's about it regarding this moon stuff. You should look up synodic periods and all that good stuff. The time required for one eclipse to repeat itself, the Saros cycle, that sort of stuff. Those are things that are relevant to astronomy, and they're just terms you sort of memorize, but you should sort of internalize them, fit them with this narrative of this model so that you can make sense of them, and use that to make sense of the actual Saros cycle and all that good stuff. Well, I hope this will help you. Again, I'll let you see this question in case anybody needs to quickly write it down. I'll leave it up there again. Remember, you can pause at any time to find out, to write something down. You can pause, write down what I say, and then, or what I write even, and then start her back up when you're ready. And here's the answer again. The answers to those questions were waning crescent, 18 days, but I would accept 15 to 20 days, any of those answers in there. 3 p.m., I would accept north, northwest, or northeast for the answer D, and this is the diagram I use to make sense of that. So hopefully that'll help you folks. Sorry no one showed up, but I hope you come back some other time and check things out and ask me questions. Send me an email if you have any problems. Have a good day.